Hello everyone, my name is Pierre Kowak and I'm going to be talking to you today about my research on the Wang-Landau simulation of the free energy surface of a crystallization in a polymer melt. Quite a mouthful, but hopefully by the end of this presentation the subject matter will become clear. So really there's a controversy in the polymer crystallization literature, and it pertains in particular to the initial stage of crystallization, whereby a quenched melt or a metastable melt below its melting point forms its initial crystalline phase. And that process is titled primary nucleation. So in particular, this is shown by the melt memory effect, or experiments that show the melt memory effect. So for example here, with the four polarized optical microscopes you're seeing on the right, those images are of crystals that were annealed at a higher temperature, melted fully, and that melting temperature that was used for the four different ones is shown on the figure, and then they're all brought back to the same crystallization temperature, and then we see these images. So basically what we're seeing here is that the melting temperature affects the final crystalline state. So we're seeing in each of those that the arrangement of the molecules is different, and therefore we have a different final crystalline state. So the naive idea is that your melting temperature should not affect your final state. Rather, your current or crystallization temperature should. So to show that, for example, look at the analogy of taking out ice from a freezer operating at -4 degrees Celsius and a freezer operating at -10 degrees Celsius. Your final water state in the liquid is not affected by which freezer it was in. But here we see exactly an example of that phenomenon. So what is the causal effect here? Is it just slow dynamics, leaving behind some crystalline states by which crystallization progresses? Or is it that there's an intermediate metastable phase between the metastable melt and the crystal that defines this? We don't know. These are other observations that basically show similar phenomena. So focusing on one of them, results from small and wide-angle X-ray scattering from Amy al. in 1995 really reveal this behavior. So focus your attention on the plot on the left talking about wax experiments or wide-angle X-ray scattering experiments. What we see is intensity plotted versus scattering angle, and we see four curves each at different dimensionless times. So for example, the initial curve denoted in circles is at 1.25 initial time, and what we see is we don't see a peak. So what do these results tell us? Basically, wax can probe angstrom scale behavior, or really behavior at the molecular level, and if we see a peak in the data, that means we have a crystal, or crystallization has occurred. So at those initial times, we don't see crystallization. And we keep not seeing crystallization all the way up to 2.84 dimensionless time, where we see a Bragg peak, which is what characterizes crystallization. Now let's focus our attention on Sachs, which shows conflicting information. Sachs on the right probes larger scale ordering on the nanometer level than the molecular level. So it's showing us larger scale ordering, or ordering on a larger scale than the wax experiments here. And what we see is similar behavior. At the initial times, there's no crystalline phase, and there's a bit of an induction period. But really, these peaks started showing up at about a third of the time that the peaks in wax showed up. So what this is telling us is that there's some sort of initial ordering on a larger level, larger scale, larger length scale, before the order we expect to see on the molecular level. And this is really an indication that there's some sort of intermediate state. So conventionally, primary nucleation is explained through the paradigm of classical nucleation theory. So focus your attention, please, here on the graph on the top right. What we see is a common free energy surface between a metastable melt, which has a higher free energy than the stable crystalline phase. So every system in nature wants to minimize its free energy. And we see the liquid and the crystal on the right at the end of the spectrums. And what happens in the middle is this liquid, or this metastable melt, is motivated by its bulk free energy to form a crystalline phase, but surface free energy opposes that movement. And what we see is this manifests as an energy barrier in the middle. And this is why we see an induction period, for example, is we need to wait long enough for a crystal with a certain size or with a certain energy grows so that it can survive. So what we see with this paradigm is really there's no intermediate phases, there's only a single barrier, and this can't directly explain some of the phenomena that we saw. So the alternative here is really inadequately summed up as the SOM hypothesis in the literature, which suggests that there's some sort of intermediate mesophase, enigmatic crystal, that exists and helps us progress from a metastable melt to a crystal. And we see that by the free energy surface on the right, on the bottom right here, where we see, again, a metastable melt with a higher free energy than the lower crystalline state on the right. But in the middle, we have two peaks, and sandwiched between them is that mesophase, is that intermediate phase that classical nucleation theory really can't predict. Now, this theory is pretty controversial, and different authors, different scientists, different researchers predict that this is due to different phenomena. So as we mentioned, some of them believe that it's the slow dynamics of the system, the entanglement dynamics, and as we've seen, the SOM hypothesis kind of says, no, it's thermodynamic. There's some sort of intermediate state that prevents us from understanding the system through classical nucleation theory. So many people have been trying to delineate who's right, and we see very smart people all over the literature from all over different diverse fields try to solve this fundamental problem, this really fundamental problem that's important to polymer processing and our understanding of polymers in general. Now, we believe that we have an interesting approach that may shed some new light on this problem. What we're going to do, or our approach, is we want to simulate bigger systems with appropriate system sizes and densities, and we want to simulate systems, simulate homogeneous nucleation from these systems, from these melt density systems, and observe the process of nucleation. And what we're going to use to characterize them is the free energy surface. So as you can see here from the figure on the bottom right, you have a hypothetical free energy surface, and if we could build it along some sort of reaction parameter or order parameter that defines crystallization from 0 to 1, we can see the melt, we can see the crystal, and we can see what's happening in the middle. So for example, here we're characterized by a single metastable phase between the amorphous melt and the crystal. So that's the advantages of using free energy surfaces. We could really directly test whether classical nucleation theory is appropriate, or SOM, or somewhere in the middle, or beyond those expectations. So it would really reveal what's going on in the system. So how does one build a free energy surface? So conventionally, the literature, rightfully so, moves towards molecular dynamic type methods like, for example, metadynamics. And the reason they do that is because molecular dynamics really provides you with the whole picture. It gives you dynamic effects or dynamic properties, and it gives you structural properties. It's also readily available. There's all sorts of different open source platforms or programs that simulate molecular dynamics, which take about 15 minutes or so to learn, like LAMPS. So it's easy to do research in this field. Well, I don't know how easy. I guess it's easy to employ these types of simulations. Of course, all sorts of molecular simulations are difficult. But the problem is that because we have to agree with or respect the laws of motion, what happens is we are really limited by entanglement dynamics. And what happens is we really need to simulate very long times, which becomes increasingly non-trivial and limits people from using this approach, especially when simulating homogeneous nucleation. However, what we've decided to implement is a Wang-Landau Monte Carlo type simulation, which allows us to break bonds, which helps us overcome entanglement dynamics. It helps us overcome energy barriers and see all of phase space. And it's a direct test of the density of states, which we can use to build a free energy surface like we want. So another important thing that we've decided to implement is parallel programming to solve our systems. So polymer simulations, as you can see from the plot on the left here, are quite complex and require a lot of time, and that time exponentially increases with increases in number density or the number of molecules. And really what we're interested in, the system we're interested in, are melt density systems, which are really at the end of that spectrum where it's really hard to simulate these systems and you need long computation times. So what we've decided to implement is a domain decomposition construct which cuts up our box into different active areas, which can then simultaneously be simulated by different threads on the GPU and therefore speed up our equilibration. We've also employed advanced movesets which help us break entanglement dynamics. So for example, from the two examples of bond breaking moves you see on the left here, there's end bridging, where you break a bond of a bead and reattach it to one of the ends, essentially making a new end and relaxing the system, moving it in a way that is non-trivial. With double bridging move, it's the same idea. You have, as you can see here by this important example, you have two bead spring molecules that are stuck together because they're entangled. And what we do is we break the bond of each of them and reattach it to the other molecule here. And what you see really is a much more relaxed system. Those molecules have much more space to move away from each other now than they had before. With configurational bias, an extremely important move that is widely applied, what we see is that we try several moves and that helps us in dense systems where it really is, there's a low probability that we accept a move due to everything being so crunched up together. So trying several moves increases our chance of acceptance, and we can unbias these biased moves at the acceptance stage. So domain decomposition is really going to help us break the simulation of volume, and let's see how. So with conventional Monte Carlo, historically it's been really hard to parallelize a system like this because it's inherently sequential. Each bead's movement is going to affect the energy of all its neighbors, and therefore moving two things simultaneously might affect our energy calculation and violate detailed balance. Now, however, with checkerboard Monte Carlo, what we do is we cut up the box to different cells, different active cells, and as long as any two active cells are at least a cutoff radius apart, we can move beads in their locations in these cells simultaneously because the cutoff radius defines that they don't interact in any non-zero way. So what we see here is that instead of moving one bead, we can move beads in 4 different cells, and that effect is multiplied several times over with bigger systems and in 3D like our systems. So this method has been innovated by Anderson et al. So a Wang-Landau Monte Carlo generated free energy surface, as we briefly mentioned before, can really show us the difference between CNT and SOM. And so the reason we've employed that to contrast it with Metropolis Monte Carlo, for example, with an acceptance rate that is really the Boltzmann probability. What happens is if you start, for example, in this hypothetical free energy surface down the center, Metropolis Monte Carlo biases us away from high energy differences and would not let us escape this sort of cage, and we can't sample phase space efficiently. So therefore, Metropolis Monte Carlo is a very bad way to build a free energy surface. Now, however, with Wang-Landau Monte Carlo, what we see is the acceptance probability biases us away from states that we visited frequently, and what that ensures is that ensures a flat histogram, and we can really sample all of phase space evenly and therefore understand all of our system and its complexity. So we have verified our results with University of Minnesota's Dr. Morse's Simpatico code, which is open source and freely available. And what you can see here through plots of the potential energy or the expected potential energy versus dimensionless temperature is that there's agreement along the different points. Now we're very happy about this result. So what you see here is speed up plotted versus the number of chains. And we were really expecting results like this, and we expect better results after we've spent some time on optimizing our code. We see 2 orders of magnitude of speed up, and the speed up is really like the time it takes to simulate one move in the serial counterpart of our code divided by the time per move in the parallel counterpart. So what this is going to help us do is it's going to help us explore systems that have never been studied before due to time constraints. So for example, as a simple example, something that would take 3 months to simulate now takes 1 day to simulate. And that really gives us access to much more complex systems, and therefore help us study appropriate systems for our study. And finally, this result is of a free energy surface built by a Wang-Landau MC simulation for a 200,000 bead system at melt density of 0.85. And what we see here is free energy versus dimensionless temperature. And hey, what we see here is a single transition characterized by the inflection at a temperature of 3, and it's a first order phase transition. And what we see on the figure on the right is their random closed packed crystals. So this observation really is troubling because it means that our work is useless and classical nucleation theory applies to this system. However, that's not necessarily true. What we're simulating here are bead rod systems which apparently don't have enough complexity to capture more complex crystallization behavior, and this is consistent with what we found in the literature. So therefore, CNT is appropriate for the system, but we predict that once we add in different segments, we should see different behavior, and CNT no longer apply, or maybe it does. So we've built a GPU-accelerated Monte Carlo code that can build a free energy surface. We used it to build a free energy surface for a bead rod system, and what we found is that chain connectivity is not enough to capture complex polymer phenomena, and therefore classical nucleation theory trivially applies to this system. Now in the future, we'd like to use our code to explore different order parameters, to add more realistic details so we can see that more complex phenomena and study it, and definitely study longer chains so we can include entanglement effects as well. Now thank you for listening. I would like to acknowledge my research group as a whole, the Tree Soft Matter Theory group at BYU. They're all lovely people and very much hard workers. I'd like to thank the American Chemical Society's Petroleum Research Fund. I'd like to thank BYU's Board of Trustees and the BYU Office of Research Computing and Fulton Supercomputing Lab for providing us with resources to do our work. Thank you for listening, and I hope you enjoyed this talk. I can do this. I can do this. I can do this. Tried 103. Thanks for watching, you guys, and I hope you enjoyed this video. If you have any questions or comments or anything like that, please post them down below in the comment section. I'll make sure to answer all of your questions and read them. Thank you.